Good morning and welcome back to the next lecture on energy conservation and waste heat recovery. So, we are talking about energy storage, and you remember in the last few lectures what we covered are three mechanical energy storage technologies: pumped hydro, compressed air energy storage and flywheel. So, today what we are going to talk about is energy storage in a magnetic field. Okay. So, that is what is called superconducting magnetic energy storage or SMES. Okay. So, let us talk about a little bit how a magnetic energy is stored. So, let us talk about an induction coil. Okay. So, this is an induction coil and let us say the induction is L and we have a current I flowing through it. Okay. Right. So, what happens to, what is the amount of energy that we can store? The amount of energy that we can store is, again let us say energy stored ES is half Li squared. Okay. So, which means again it is proportional to the square of the current. Remember in flywheel it was what, half I omega squared. So, a similar form, there it was proportional to omega squared, and we said that we want very high angular speed, we have to store high amount of energy. So, here also we would say that it is desirable to have very high current. Okay. So, I would say it is desirable to have high current or I. Now, what is the problem? However, the problem is there is also an energy loss due to Joule heating, and that is equal to I R squared. Clear? So, which means that Joule heating also goes up if I increase I, because you have a finite resistance R. So, on one hand if we want to store more energy in a magnetic field, we need high current, but then what acts as a detrimental factor is the Joule heat, which also goes up because of current or with current. So, this is where the problem is. So, the way this is solved is to solve this problem, we use superconducting magnetic coil. Clear? Now, what is a superconducting magnetic coil? Okay. So, here materials, when they come close to 0 degrees absolute or Kelvin, there are certain materials whose electrical resistance goes to 0. Okay. I am not saying close to 0, it is 0, they just there is no resistance, that is why it is called a superconductor. Okay. So, what is the feature? Let me write it down, is resistance R equals to 0 when temperature falls to Tc, which is a critical temperature, which is around 0 Kelvin. I am not exactly 0, but close to 0. It is not easy to do, but this is the material, or this is the material, and this is its unique characteristic of a superconducting material. Okay. So, therefore, what happens now? Let us talk about it. If I again draw the magnetic coil over here, okay, and I have a current I flowing through it, this is L. All right. Now, in case 1, what I will do is, stage 1 is I will apply a voltage E across it. Okay. So, first what I would do is apply voltage E across the superconducting coil. Then what happens? We know that E is equal to L di dt or d tau, where tau is time. Okay. So, therefore, what will happen? Let me draw something. I am going to draw the current with respect to time. So, in the first stage, what happens? E is equal to L di dt. Therefore, di dt is E over L, which is linear, and therefore, the current will increase from 0 linearly to some value, okay, and we call it, let us say, I target. Okay. So, therefore, current increases linearly to I t, and energy stored okay. What I will do is I will just change this the nomenclature from E to V, and here also I will write it as V. Okay. The reason is I do not want to confuse it, or I do not want to confuse this EMF with the energy storage by using the same symbol E. Okay. So, the energy stored is going to be half L I t squared, okay, at this point. So, at this point what we do is we, so I will use 3 different colors. At this point I will use the green color, we short the circuit. Okay. So, stage 2, what happens is this coil or the circuit is shorted using a switch, and this switch also should have 0 resistance. So, made of superconducting material. So, it is a superconducting switch. So, therefore, what happens? This current keeps flowing through this circuit, all right. So, therefore, here what happens is the current remains constant. Okay. So, this current will remain constant. Then what happens if I now want to retrieve the energy out? Then in that case what I will do is I will have a third one where I am going to reverse the polarity and make the current flow in the opposite direction. Okay. So, at stage 3 when we wish to extract energy stored in the inductor or coil, we reverse the polarity of the EMF applied or supplied. Then what happens? The current will reduce. Okay, here I will use the black ink only. So, current reduces, and how does it reduce? It reduces like this. Okay. The variation is going to be exponential. Okay, and why? Please, I would give it to you as a home assignment or whatever, a little self assignment. It is very easy. Why it should reduce or in not in linear but exponential manner should come automatically. Okay. So, if this is the case, then what happens is I will write the 3 stages. So, this is charging, this is storage, this is discharging. Okay. So, this is how it works. So, therefore, when we have additional energy we supply it, okay, we supply a voltage and it goes up. When we want to store it, we just remove it and short the circuit. When we want to get it out, we reverse the polarity of the EMF applied, and then what happens, we add a of course we will add a resistance through which we want to get the current out of it. All right. So, if this is the case, then let us look at this slide now, and it is going to become a little clear. You have a power system and a power conditioning system. So, all these things that we talked about, which is supplying the voltage, reversing the polarity, shorting it, these are all done using a power converter circuit. So, that is what is shown here, that the power electronic circuit does the analog to digital conversion, it varies the voltage, it reverses polarity and everything. Okay. The discharge happens on reversal of polarity. I am going down up here because we have discussed all these, and the first two of course we see that. Okay. The other thing to note is the superconducting coil has to be maintained at a very low temperature. So, as a result we would need a cryogenic system rather. Okay. Refrigerate, I have written it, or the figure over there which I have borrowed from the source says it refrigeration system, but I would say but actually it falls in the cryogenics range. Okay. Now, what is the material that is used? What are some of the materials? So, superconducting material, the one that we most commonly know is actually a molybdenum, Niobium, titanium wire. Okay. But however, what is happening is these days the niobium titanium, as is shown in the over here, the critical temperature is close to 0. So, it requires liquid helium. But what has happened is new development is that recently we have been able to, or some labs have been able to develop materials which have which show superconducting behavior at higher temperatures, that is like 100 Kelvin. It is still below 0 degrees, still you need still need refrigeration, but here you can use liquid nitrogen instead of liquid helium. So, it is simpler cryogenics, nitrogen is available in abundance, we have established technologies to liquefy nitrogen. So, the cryogenics are much simpler compared to liquid helium. So, that is why this high Tc material is also being used. But however, typically what has happened is the high Tc material is still under development. So, small units, small energy storage has been shown to work, but if you go to slightly higher values of energy that you need to store, it is still niobium titanium that we are using. Okay. What else? The other thing that I want to show is about the construction. So, we drew a simple magnetic coil, all right, and we said that at one point we will discharge, at one point we will charge, then during discharging again we will have reverse the polarity. So, what is going to happen? Okay. What is going to happen is, as the current changes during the discharging cycle, let us talk about discharging cycle right now. As the current changes, the magnetic field strength will also change. So, now think of me as a person or any living person or even the atmosphere. What is happening? Around it there will be a magnetic field that is generated, whose intensity will be varying. Okay. Now, let us say I stand and human body is a conductor, then what happens? There will be a voltage established across my body and which is going to be fatal, right, correct. It is a varying magnetic field in a conductor in a varying magnetic field. So, therefore, what is typically done is we use a toroidal structure, as I am showing here in the slide, that for wound coils, for smaller energy storage the regular coil is probably okay, for short term requirement for stabilizing a cycle, stabilizing a circuit, it is okay. For the larger systems, what we have to do is, instead of just having a regular magnetic coil, we will have it in the form of a toroidal structure. This way, and what happens here is the coil is wound round this structure, all right. So, this is the toroidal structure. So, I would say is for higher power systems, and what this does is the magnetic field is constrained. Okay. So, no varying magnetic field outside, clear. This is also a very strong and stable construction. Because you see we have, I do not know how many of you have had the experience of going through an MRI scan. Okay. In an MRI scan, what happens is you have these large magnetic coils and which is continuously magnetized and demagnetized. Okay. And as a result of that, I mean, one of the, if you have gone through it, or if any of your friends or relatives have gone through it, if you ask them, an MRI scan is a very painful experience because there is a tremendous deafening hammering noise that the patient has to withstand for the duration of the scan, which is typically around 20-25 minutes. It's extremely painful because you first go into the tunnel, which gives you a claustrophobic feeling, and then you have this hammering noise all around you. Okay. The reason this happens is because of the repeated magnetization and demagnetization, there are mechanical forces that arise which are known as the Lorentz force. Okay. And that leads to, this Lorentz force happens between two adjacent conductors, and in this case maybe two of these windings, adjacent windings. All right. So, such things, even here also you have a varying magnetic field. It may not be from 0 to a certain magnetic field in a step function or close to a step function, that is what happens in an MRI scanner. But here also there is a varying magnetic field, so there will be Lorentz forces, and these Lorentz forces have to be withstood. So, for higher power systems, this toroidal structure also helps in withstanding the or the mechanical forces which are the Lorentz forces. All right. So, again, to summarize, I will just take help of this schematic on this slide. What we have is a superconducting magnetic coil. What is a superconducting magnetic coil? A superconducting magnetic coil is made of a material whose electrical resistance goes to 0. Okay, it just does not exist below a certain temperature, which is corresponding to which is a critical temperature corresponding to that material. So, we make use of that. So, we have a superconducting coil. So, this material has to be refrigerated and cooled down to below its critical temperature. If we now have that, then what happens is, if we now apply a voltage across that coil, what happens is there is a charging cycle. During the charging cycle, the current through the coil increases linearly until it reaches a certain target or threshold value, which is the amount of energy that I want to store. Okay. And what is that energy that I am going to store? Is given by half Li squared, and here I is the target current where I have stopped. So, at that point I stop charging the circuit anymore and instead short the coil by using a superconducting switch. The wire and the switch has to be made of superconducting material again. So, therefore, what happens is, we have a superconducting coil through which a current flows or keeps flowing, and therefore, the energy equal to half Li squared, and in this case I is the target current where I had stopped, is now stored. It is not discharged, it is stored. So, that is the energy storage system that we have. When I want to take energy out of that, what we do is, we have the current flow through in the reverse direction, and the way to do that is, again, attach an EMF source with reverse polarity. Okay. And then and then in the same circuit you put the resistance across which you want to flow current, you want the current to flow, and thereby extract that energy out. Okay. So, if you do that, then the current in the discharging cycle falls from the target value to which I had charged it, and it falls down as it flows through that, or as the discharging cycle continues. Okay. And we are able to extract electrical energy out of it, and which we can use for some useful purpose that we want to or use it where I need additional electricity. Now, keep in mind, these are all DC. Okay. So, we need a power converter circuit which will convert the DC to AC during generation if I want AC power, or during the charging also if the supply is AC, right. So, all that is done using a power converter circuit which takes care of everything, which has a superconducting switch in between, which does the A to D conversion and which also does the reversal of polarity and so on and so forth. Okay. So, this is the whole principle of how a magnetic energy storage system works, or superconducting magnetic energy storage system works. Okay. Next, what we talked about was the magnetic construction. We said that for small energy storage systems, if you want to just use it for stabilizing circuits, short term requirements, then a regular coil the way we described is okay. But if you want to go for larger systems, the problem is during the discharging cycle you have a varying magnetic field across in the outside, and which can be fatal if a human or a living being comes in contact. Our bodies do conduct electricity, then that can be fatal. So, therefore, we use a toroidal structure as I drew it on this picture over here. The toroidal structure, the way it helps is, it number one contains the magnetic field and does not let it go outside, and secondly it also adds strength and it is a stable construction. It is able to withstand the mechanical forces, the Lorentz forces that we talked about. Okay. And another thing that we discussed is about the materials. So, niobium titanium has been traditionally used, but its critical temperature is close to 0 absolute, which is, one can never, third law says one can never achieve that. So, we use liquid helium and we go close to that, right. So, high Tc material, the recent developments have been for materials, one of them yttrium, barium, copper oxide. This has a critical temperature of about 100 Kelvin, which is much easily attainable, and where we do not need liquid helium. Helium itself is an inert gas, it is a rare gas, it is not very abundantly available. But in high temperature or high critical temperature materials, high Tc materials, we can use liquid nitrogen, which is abundantly available, where we have established techniques for liquefaction, and therefore, the cryogenics is going to be way simpler. Okay. All right. So, that kind of brings us to the end of our discussion on superconducting magnetic energy storage. So, with this, what we have studied so far under energy storage are 3 mechanical technologies: pumped hydro, compressed air and flywheel, and then the fourth one is magnetic energy storage. So far we have learned about, in the last I think 5 lectures, we have covered 4 different technologies for energy storage, all of them very interesting, exciting, and all of them are used, especially like pumped hydro, flywheels, these are abundantly used. Compressed air superconducting magnetic energy storage is also used, maybe not so wide, the application is not as widespread as others, but still it is used. Okay. So, what we will do in the next lecture, we will continue this discussion on energy storage systems, and we will start with something called thermal energy storage systems, where the energy is stored in the form of thermal energy. Okay. All right. Thank you very much and see you in the next lecture.